Hi, this is Lucas Zipp. I'm a researcher at SRI International, and in this talk I'm going to give an overview of some of the work we have been doing in building a time and wavelength multiplexed photonic reservoir computer. I'm sure other talks will go into more details on the theoretical aspects of reservoir computing, so I'll keep the introduction to the topic very brief. Essentially, a reservoir computer, which is also known as an echo state network or a liquid state machine, is a type of recurrent neural network that consists of a reservoir of internal nodes with fixed untrained recurrent connections, which are then coupled out with the linear matrix multiplication readout layer. The three distinguishing characteristics of a reservoir computer are its large dimensionality, in other words, how many internal nodes the reservoir contains, some form of nonlinearity which is applied to the signal either within the reservoir or at its output, and finally some level of memory capacity or memory depth to the reservoir, which allows it to classify or filter signals based on its past history. One of the key advantages of the reservoir computer is that only the final readout weights are trained, using linear regression techniques. This greatly simplifies the training process of the network. In addition, the single output layer allows for lower latency computation compared to deep neural networks. Potential applications for reservoir computers include time series prediction, speech recognition, nonlinear channel equalization in free space communication networks, as well as low latency internet data packet analysis and filtering. The simple structure of a reservoir computer, with its untrained internal connections, has allowed for its implementation in various analog physical systems. In particular, its implementation in an optical or photonic system is very enticing, because photonics has several advantages over electronic processors, including the ability to simultaneously process several terahertz of bandwidth on a single physical node, very low propagation losses of high bandwidth signals, and the ability to perform parallel processing via wavelength multiplexing. The types of photonic reservoir computers that have been demonstrated can be loosely categorized into three different types. The first is a delay-based time multiplexing approach, first in an optoelectronic design in 2012, and then in an all-optical coherent design in 2015. The basic idea behind the delay-based time multiplexed reservoir is that a single delay loop is used for the reservoir, and virtual nodes are created by modulating the input signal with fixed repeating amplitude weights. The second class of photonic reservoirs is a spatial reservoir, which is a direct mapping of the reservoir nodes and connections into a spatial network of optical connections. This was demonstrated in a passive network on a silicon photonics chip in 2014. A third type of photonic reservoir is a wavelength-multiplexed reservoir, which encodes the reservoir dynamics through the mixing of individual wavelength channels in a single delay loop, as was demonstrated by Akrut and coworkers. Looking at the broader picture of the state of photonic reservoir computing, we want to push the capabilities of photonic reservoir computers to a point where they can outperform silicon-based digital AI processors. The main limitation of previously demonstrated photonic reservoirs is that they don't have sufficient complexity or functionality to compete directly against state-of-the-art neural network techniques. Photonic reservoir computers have already shown the ability to perform highly efficient, low-latency computations, but their functionality has been limited to performing relatively simple computations, like simple speech recognition tasks or bit pattern correlation, but our goal is to extend the functionality of photonic reservoirs so that they can compete directly against state-of-the-art AI processors on complex real-world problems. So how do we get to this increased functionality? As I described earlier, there are three basic elements or characteristics that describe a reservoir computer: its dimensionality, the form of nonlinearity, and its memory capacity. The element that we are most focused on improving is increasing the dimensionality or effective size of the reservoir. This will allow us to achieve better performance on complex tasks, which we will demonstrate later in the talk. I'll cover three general areas in discussing our work. First, I'll describe in more detail our photonic reservoir design and our methods for modeling and simulating the reservoir performance. Next, I'll cover some of our simulated results on some performance benchmarking tasks, and finally I'll conclude with some preliminary progress on our experimental prototype. Our overall system architecture takes advantage of the combined use of both time and wavelength multiplexing. The use of wavelength multiplexing allows for an increase in the number of effective nodes that can be processed by the reservoir, with minimal increases in hardware complexity and power consumption. When combined with time multiplexing, this allows for a relatively large effective reservoir to be implemented on a single physical hardware node. The input to the reservoir can be taken directly from an optical fiber input, or it can be an electronic digital input that is modulated onto an external optical carrier. This optical input is then modulated by an input mask, which initiates the time multiplexing in the system. This input signal is then fed into the reservoir feedback loop, which contains a phase modulator for achieving spectral comb generation and mixing, following the method of Recruit and coworkers. The number of effective nodes in the reservoir is equal to the number of time multiplexed nodes multiplied by the number of wavelength multiplexed nodes. And the number of time multiplexed nodes is constrained by the readout rate of the ADC, while the number of wavelength multiplexed nodes is ultimately limited only by the bandwidth of light supported by the photonic components. In general, this will ultimately allow for hundreds or thousands of virtual nodes in the reservoir. As the signal circulates through the reservoir loop, on each iteration the signal deforms in both time and spectrum as it propagates in the multidimensional space of the reservoir. Some of the signal is outcoupled and demultiplexed, where it is then read out and digitized by an array of photodiodes and ADCs. The readout of the spectral comb can be performed with a separate photodiode for each wavelength as depicted here, but we are also exploring weighting and recombining the spectral nodes entirely in the optical domain, which would reduce the digital processing load. So this slide explains in a bit more detail the comb generation and spectral mixing process that is induced by the phase modulator. When a phase modulator is driven with a sinusoidal input, it will generate sidebands around the carrier frequency, whose amplitudes are described by the well-known Jacobi-Unger expansion in terms of Bessel functions. In general, the larger the phase modulation amplitude, the greater the number of sidebands that are generated. This comb generation process allows for fully parallel computation within the reservoir and directly increases the size of the reservoir itself. Beyond that, on each iteration of the signal through the delay loop, each spectral channel becomes a source for new sideband generation, which mixes with the pre-existing spectral channels. This additional spectral mixing adds to the internal complexity of the reservoir dynamics. The wavelength multiplexing method possesses two distinct advantages over time multiplexing. The first is that it increases the reservoir size without increasing the required electro-optical modulation and readout rates of the system. In the case of the time multiplexing approach, the required rates scale proportionally with the number of virtual time nodes. This isn't the case for a wavelength multiplex design, with each spectral channel operating in parallel. The second advantage is that it allows for mixing of non-adjacent nodes. In a pure time multiplex design, only adjacent nodes are connected on each iteration in the signal through the reservoir loop, which limits the dynamics of the reservoir. In the wavelength multiplex version, several nodes are simultaneously connected based on the Jacobi-Unger expansion, which enhances the richness and complexity of the reservoir dynamics. This is a flow diagram of the processing steps that occur in simulating the operation of the reservoir computer on a set of classification tasks. We start with a set of input data which may have some classification labels associated with it. We then apply a repeating amplitude mask to the input data to apply the time multiplexing. This is then fed into a model of the reservoir delay loop, and the output of this loop is fed into a training algorithm which produces the optimized weights of the linear readout matrix. After this training step, the output weight matrix is then applied to the reservoir output and its classification accuracy is tested. The full reservoir dynamics of the optical field are described by the equation shown here, which incorporates the phase modulator and delay loop dynamics. The sign term that you see there accounts for the impact of the sign dependency of the Mach-Zehnder modulator amplitude modulation onto the optical carrier. A precompensation can also be applied to the signal input to remove that sinusoidal dependency and to achieve a purely linear modulation. An important note is that the use of the analytic Jacobi-Unger expansion for modeling the effects of the phase modulator is essential for getting reasonable runtimes for the reservoir simulations. We estimate that we get about a 500x speedup over a purely time domain model of the wavelength-multiplexed reservoir. An important aspect of reservoir computers is that the performance can vary dramatically with tuning of the system hyperparameters. This table displays the various system parameters of the photonic reservoir computer that can be varied, as well as their nominal ranges. In order to achieve optimal performance on a particular classification or time series prediction task, we must optimize over all of these parameters. The exception is the round-trip delay time, which is fixed by the physical length of the fiber delay loop. We fix this value at n+1/n times t, where n is the number of time nodes and t is the period of the input data stream. This value was found to achieve good results on our performance tests and agrees with the previous results in the literature. When looping over the system hyperparameters and calculating the normalized mean squared error at each parameter set, you quickly find that the dependence on the hyperparameter values is not guaranteed to be convex. This leads us to take a more brute force approach to the optimization, where we systematically loop over all system parameters to make sure that we have mapped out the parameter space with a sufficient degree of resolution and that we aren't missing the global minimum. In the future, more efficient optimization methods could be used to reduce the time needed to find the best operating point of the system for each specific computing task. Now I will cover some of the results of the time and wavelength multiplexed reservoir and some performance benchmarking tasks. The first one we consider is the NARMA 10 task, which is frequently used in reservoir computing studies. In this task, a nonlinear time series is generated, which takes a randomly generated input u of t and produces an output y of t that includes a nonlinear sum of the 10 previous inputs to the system. The goal of the task is for the reservoir computer to learn this nonlinear time series function based only on a knowledge of a finite set of inputs and outputs to the time series function. In our case, we generated a 2,000 sample sequence and trained the reservoir on the first 1,000 samples of the sequence and tested the reservoir performance on the remaining 1,000 samples. In each case, we optimized over the loop gain alpha, the round-trip phase, and the phase modulator voltage amplitude. An example of the NARMA 10 output and its estimate by the reservoir computer is shown on the right. The reservoir prediction is shown in red against the actual values in blue for the case of a normalized mean squared error of 0.34. We ran the photonic reservoir model on the NARMA 10 task and looked at the resulting performance as a function of the number of time nodes as well as the number of spectral channels. We found that the wavelength multiplexing improved the reservoir performance, and that as the number of spectral channels was increased, the normalized mean squared error was reduced. This benefit was seen to hold for all values of the number of time nodes that we included. Another way of thinking about the benefits of the wavelength multiplexing is that we can achieve a desired performance accuracy, say an NMSC of 0.1, with far fewer time nodes required. This is advantageous for the photonic reservoir system, since the number of time nodes is ultimately limited by the electronic bandwidth of the system. We then looked at the reservoir's performance on a simple IP packet classification task based on the IP header field, where the reservoir acts as a sort of optical firewall on an incoming binary data stream. This classification problem is slightly different than the time series prediction, since this is a many-to-one RNN problem, rather than a one-to-one problem. The simple packet classification task that we looked at was to classify incoming packets based on valid source and destination port addresses for HTTPS traffic. The filter rule set is shown in the table, and although it's a simple rule set, it is already a nonlinear classification problem, which we can see in this schematic in the bottom left. So packets that lie in the blue region we want to label as a pass, while all other packets in this space we want to drop. In this task, rather than associating all the time nodes with a single input bit, as we did for the time series prediction task, here the time nodes are extended over multiple bits in the header field, which we call a multi-bit encoding scheme. This leverages the fact that this is a many-to-one classification problem. We trained the reservoir on 3,000 simulated IP packets and then tested on an additional 3,000 packets, performing full optimization sweeps on the gain, round-trip phase, and the phase modulator amplitude, just as we did in the time series prediction task. Here are results for the simulated performance on the IP packet classification task. We see a similar pattern where the reservoir performance improves rapidly with an increasing number of spectral channels. The classification error rate is shown in the upper right, and we see that the error rate quickly falls to extremely small values for multiple spectral channels. In the case of 5 spectral channels and 5 time nodes per bit, only 2 packets out of the 3,000 test packets are misclassified, which is shown graphically in the scatter plot. So in this simple packet classification task, the reservoir computer performs very well. We are also looking at ways to additionally improve the performance of the photonic reservoir design. And one aspect that we are looking into is the addition of a second harmonic tone in the phase modulation in order to break the symmetry of the spectral mixing. When the phase modulator is driven by a single frequency tone, the sideband generation process is symmetric about the center frequency, as seen in the upper row. When a second harmonic driving tone is added, the symmetry of the sideband generation is broken, as you can see in the bottom row. Breaking the symmetry of the spectral mixing process removes redundancy from the reservoir system and should further increase the complexity of the reservoir dynamics. So we tested the addition of this 2 omega driving field in our simulations, and we found that it did in fact improve performance on the NARMA 10 time series prediction task. For a single channel, the results are unchanged as expected, but we see some modest improvements in the case of 3 and 5 spectral channels. The addition of the second driving frequency does add 2 more additional hyperparameters to the reservoir system, which does increase the parameter space that needs to be optimized over. Now I'll briefly discuss some of our preliminary work on building an experimental prototype of the photonic reservoir computer. Before building the full time and wavelength multiplexed reservoir, we are starting with a simpler, purely time multiplex coherent reservoir design, which has been successfully demonstrated previously by Vinkier and coworkers. We use a 100-meter long cavity fiber loop and read out the results of the reservoir on a photodiode, which is sent to an analog to digital converter, and the final matrix multiplication step is then performed in the digital domain. The nonlinearity in the reservoir is provided solely by the quadratic nature of the intensity readout on the photodiode. Since the photonic reservoir design is coherent, it is sensitive to phase shifts within the cavity loop from environmental noise, predominantly from thermal and vibrational disturbances. A way to control these phase shifts was demonstrated by Vinkier and coworkers by using a counter-propagating beam as a reference to measure the internal phase shift of the cavity. A PID loop is then used to control and stabilize the round-trip phase of the loop through an applied voltage to a phase shifter placed inside the cavity. The essence of this phase control method relies on the fact that we can launch the signal in the reference beam into orthogonal polarization eigenmodes of the cavity loop through a pair of polarization controllers. Each polarization eigenmode will pick up a distinct transmission phase shift as it traverses the cavity. This difference in phases can be easily seen in the cavity transmission resonances when sweeping the round-trip phase of the loop, as seen in this simulated example. A third polarization controller placed within the loop allows us to control this phase offset between reference and signal, so that any arbitrary round-trip phase can be set for the signal, while simultaneously locking onto the transmission peak of the reference. And finally, here are some preliminary outputs for the NARMA 10 time series prediction task on our purely time multiplex coherent photonic reservoir. After performing some vibration and thermal isolation for the system to reduce high-frequency phase noise in the cavity loop, we're able to achieve an NMSE in the range of 0.3 to 0.5 for 10 time nodes. This is not quite yet at the theoretical performance limit of our simulations, but we are getting close. The plot on the left shows the time multiplexed input and output to the reservoir system on the NARMA 10 task, while the plot on the right shows the reservoir output prediction for a specific time series example. You can see that already with the normalized mean squared error of 0.3, that the predictive power of the reservoir computer is already quite high. So in summary, a combined time and wavelength multiplexed reservoir computer allows for improved reservoir performance without greatly increasing the footprint of the system, which we have demonstrated through simulations on a time series prediction and data packet classification task. We are also making progress towards implementing this design in an experimental benchtop prototype. Some directions that we are also exploring are designing a wavelength multiplexed reservoir that is compatible with photonic integrated circuit components so that we can scale the footprint of the system down as well as reduce the energy consumption of its components. Another area that we are investigating is the inclusion of additional nonlinearities into the reservoir in order to increase the complexity of the reservoir dynamics. So hopefully this talk gives you a little bit of overview on the field of photonic reservoir computing and our work towards building a combined time and wavelength multiplexed reservoir computer.